let's discuss fluid in motion. So now viscosity. Okay, so what is viscosity? So just like in case of solids, we have friction. Okay, so suppose we have a solid body. For an example, suppose there is a block resting on a floor and we want to push, sorry, suppose there is a block resting on a floor and we want to push that block. Then there is some frictional force which resists the sliding motion of that block on the floor. So just like that, there is friction in fluids also. So see what happens here is, now suppose there is this fluid in this pipe. Okay, so when the fluid moves, what happens is different, you can assume there are different layers of fluid and one layer slides above another layer. Okay, one layer slides above another layer, right? So if you consider some river, suppose, so in that river, the layer at the bottom, it is in contact with sand. So layer of the water, which is at the bottom, it is in contact with land or sand, you can say. Okay, so now the sand or soil, you can say, it doesn't want that water to move, to slide. Okay, because if it wants to move, if river has to flow, then water has to move. Okay, that means it has to slide above that line. Okay, so now therefore that layer, the layer at the bottom, it will move with least possible velocity. Okay, the velocity of that layer at the bottom would be least. Then layer above that, it will move with little bit higher velocity. Then layer above that, it will move with even more higher velocity. Okay, so on and so forth, right? So layer which is at the top, its velocity would be highest. Okay, is this thing clear? Yes, no? So now there is some difference in velocities of layers. Okay, so that we call as velocity gradient. So what is velocity gradient? It is change in velocity per unit distance. Okay, so suppose you take an example of a river. So the topmost layer, it will move with highest velocity. As you go down, what happens? The velocity goes on decreasing. Okay, and the layer at the bottom, it moves with least possible velocity. Suppose you consider a block kept on a table and you want to move it. So there would be a frictional force between that block and the table surface. So just like that, there is frictional force between different layers of the liquid also or fluid also. So that frictional force is known as viscosity. So what is viscosity? It is the internal friction, okay, between the two adjacent layers of a fluid in motion. What is viscosity? It is the internal friction between two adjacent layers of fluid in motion. Okay, so now there are certain laws for viscosity. So there is again Newton's law of viscosity. So Newton says that the viscous force F, it is directly proportional to the area of the two layers in contact, and it is inversely proportional to, sorry, it is directly proportional to the dv by dx, that is velocity gradient. Okay, so viscous force is directly proportional to area of contact between the two layers. Okay, and it is directly proportional to the velocity gradient, right? Then again, if you combine these two, then what do you get? You get A times dv by dx. So the viscous force is proportional to A times dv by dx, and if you remove the proportionality sign, put an equality sign, a constant will enter. So constant here, it is known as the coefficient of viscosity. Okay, the constant here, it is known as what? The coefficient of viscosity. It's denoted by letter eta. Okay, so now, so if coefficient of viscosity is more, that means there would be less internal motion in a fluid. If coefficient of viscosity is more, then more internal motion is possible. Okay, for an example, if you take two fluids, one is water, one is honey. Okay, so water is less viscous compared to that of honey. So suppose you pour some water on a table, it spreads faster compared to that of what? Honey. Suppose you pour some honey, it will take a lot of time to spread it. Okay, and it won't even spread up to much larger distance. So honey takes longer time. Why? Because there is less internal motion between the different layers of honey compared to that of water. So honey is more viscous, right? This thing is clear? Yes, no? All right. So Newton's law of viscosity, viscous force is equal to what? Eta. Eta is the coefficient of viscosity multiplied by area of contact between two layers, two surfaces of liquid, you can say, two adjacent layers, and multiplied by dV by dx. dV by dx is the velocity gradient. Okay. After that, next comes the Stokes law of viscosity. So Newton's law of viscosity, it is general law, and it is applicable to what? Two layers in contact, two layers of the liquid in contact with each other. Next is, suppose there is some solid object moving through a fluid. Okay, suppose there is some solid object moving through a fluid, then now the fluid will also exert a viscous force on that object. Okay, just like fluid exerts a viscous force on its internal layers, right? Different layers exert frictional force or viscous force on the internal layers of fluid. So just like that, it will also exert some force, okay, frictional force on a solid object moving through a fluid. Okay, so for that we have a law called as Stokes law of viscosity. So Stokes law of viscosity says that suppose you have a spherical object moving through a fluid, okay, then the viscous force acting on that object moving through the fluid, F is equal to 6 pi eta RV. Now we just need to remember this formula, that it is equal to 6 pi eta RV. Okay, now this can be partly proved using dimensional analysis, but we will not go into that. Of course, if this equation is there, the dimensions will match, right? So is the formula clear? What is R? What is eta? Eta is coefficient of viscosity. What is R? R is the radius, okay, radius of this object, or you can say size of the object. And what is V? So object is moving with speed V. If object having size r, that means radius r, is moving with speed v through a viscous fluid, then the force, the opposing force acting on that object is equal to what? 6 pi eta rv. This is the formula. Okay, is it clear, everyone? Right, good. So now next, suppose an object is moving through a fluid. So for an example, suppose let's take a raindrop, okay, which is falling through air. What happens is, initially its speed would be 0, and because of gravity, what will happen? Its speed will go on increasing, right? But then there is the viscous force due to the air, okay, because of which its speed would decrease. Decrease means there will be opposition to its flow, okay, so the acceleration would decrease, right? Because the viscous force is directly proportional to what? Velocity. If velocity increases, that means there would be opposing viscous force. So now at some point what will happen? This gravitational force and the viscous force, and there is also buoyant force, okay, buoyant force also, they will balance, and that object, for an example the raindrop, will move with a constant velocity. That velocity is known as terminal velocity, okay, that velocity is known as what? Terminal velocity. So now we are going to see an equation for the terminal velocity. So see, for an example, suppose you have this very long cylinder, okay, made up of some fluid, and you drop some ball, okay, a spherical ball in this fluid. So initially when you drop it, its speed would be 0, okay, its initial speed is equal to 0. So then there is some gravitational force acting on it, okay, and at the moment you release it, there is a buoyant force due to the fluid acting upwards, right? In last class we studied Archimedes principle. So there is a buoyant force equal to what? Suppose this whole complete ball, it is immersed in the fluid, then the buoyant force acting on it, it's equal to what? Weight of the fluid displaced by it, okay, right, we know that. So then there is gravitational force, there is a buoyant force. So if gravitational force is more than buoyant force, then what will happen? It will begin to move, Okay, so if it is some object which floats in that fluid, then it won't have any terminal velocity, it will stop there only, right? But if it is an object heavier than fluid, means object whose density is more than the fluid, then what will happen? It will move down, right? And then once it moves down with some velocity, okay, it attains some velocity, then viscous force will also begin to act on it. It will also resist its motion. Is this thing clear? Yes, no? Okay. Once it begins to move, there will be a viscous force due to the fluid acting on it, and the viscous force is given by the Stokes law. Okay. So now what happens is, initially suppose the gravitational force is more, that means its weight is more compared to these two forces, the buoyant force and viscous force. But then as its velocity increases, buoyant force will remain same, but the viscous force is directly proportional to velocity. So as its velocity increases, the viscous force will go on increasing, and at some point, let's say here, what will happen, that these two forces, okay, become equal to the gravitational force. These two forces means sum of those two forces. So total upward force becomes equal to total downward force. So net force on that ball would be equal to 0, and then it moves with a constant velocity. Why constant velocity? Because if net force is 0, acceleration becomes 0. So it moves with constant velocity. It is known as terminal velocity, right? So the formula for terminal velocity is equal to, terminal velocity is equal to 2 by 9, okay, density of this ball, density of the object minus density of fluid times r square g divided by eta. Okay, this is the formula. We will see a derivation in brief, but this is the formula that we need to remember. Okay, so we need to remember when will it move, right? If its density is more compared to that of density of the fluid, then it will move. Okay, and we'll also need to remember this formula. The terminal velocity is equal to what? 2 by 9 rho minus sigma. What is rho? What is sigma? Rho is density of the ball or the object that's moving through the fluid, and sigma is the density of the fluid. Okay, this thing times r square g upon eta. Is this thing clear? Right. Okay, good. Then, so as we discussed at the beginning, what will happen? The gravitational force would be more, that means weight of the object would be more compared to that of what? The buoyant force and the viscous force. Okay, so it has some acceleration. So there comes a point where what happens? Net upward force becomes equal to net downward force. So net upward force is buoyant force plus viscous force, and it's equal to mg, right? That is equal to net downward force. So net downward force is mg. So what is buoyant force? So buoyant force is equal to sigma multiplied by volume of the object, because volume of the fluid displaced, because the object is moving through the fluid. So volume of the fluid displaced would be equal to what? Just equal to volume of the object, right, times acceleration due to gravity. This is the buoyant force. Then for viscous force, you have the formula, it is 6 pi eta r v. But now, as we said that two forces, the net upward force and net downward force, become equal, so the velocity attained is called as terminal velocity. So that's why we put vt, okay, in place of v. So then now we do some simplification, right? So what kind of simplification? You can move this term on other side. Okay, what do we get? So you will get 6 pi eta r vt, it's equal to v times g, you can take common, v times g multiplied by, you have rho minus sigma, right? And then you put then you put volume. Volume is 4 by 3 pi r cube, right? So you get rho minus sigma 4 by 3 pi r cube times g, and then there is just some then there is just some cancellation. Okay, some cancellation will lead to this formula. Okay, that is pi will get cancelled, right? This r cube, I mean, if you divide r cube by r, you will get r square. Okay, so then you get this formula, Vt is equal to 2 by 9 rho minus sigma r square g divided by eta. So derivation is very, very simple, right? So we need to remember this formula. Is the derivation clear? Yes, no? Of course, nobody will ask you in exam, but this is just part of understanding what's happening. Okay. So then let us see some problems based on the terminal velocity. Okay, then we'll move on to the next topic. So let's see this one. A small metal sphere of radius a is falling with velocity v through vertical column of a viscous liquid. If the coefficient of viscosity of the liquid is eta, then the sphere encounters an opposing force of, tell me. Option A, we just saw this, it is just Stokes' law, right? The radius of the sphere is a, so the force would be 6 pi eta multiplied by AV. Okay, in place of R you have A, so it's option C, right? So then see here, they have only given the viscous force, okay, and they have not given buoyant force. But if there is some option with the viscous force as well as a buoyant force, then you should choose that option. Okay, because buoyant force, if an object is falling through a fluid, buoyant force will also oppose its motion, right? This thing is clear? Okay, everyone, good. Let's see next one. Two equal drops of water are falling through air with a steady velocity v. If the drops coalesced, what will be the new velocity? Tell me. Okay, so terminal velocity is v. What's given? Terminal velocity is v. So we know v is equal to 2 by 9 rho minus sigma r square g divided by, okay, one is my 9 and another one is g, okay, divided by eta. So v is directly proportional to r square. See, if these are drops of water, okay, they coalesce, that means they combine, then the density will not change. So density will remain constant. Sigma is the density of air, it will remain constant. Eta is the coefficient of viscosity of air, okay, it is also constant. Then you have r square g. So what changes? Only r will change, right? What we can say is v is directly proportional to r square. Okay, so now when two drops coalesce to form a bigger drop, so what can we say is volume of a bigger drop, volume of big drop is equal to n times of volume of small drop. Now we'll find out a relation, so you will just remember that relation. Okay, so this is 4 by 3 pi r cube is suppose volume of a big drop, it's equal to n times of volume of small drop. Okay, so volume of one small drop is 4 by 3 pi multiplied by small r cube. Take cube root on both sides, so what do you get? 4 by 3 pi, 4 by 3 pi gets cancelled, then you get capital R is equal to n raised to 1 by 3 times small r. Okay, so hence this point onwards, whenever this thing will come, the two drops or two spheres, they coalesce to form a bigger sphere, then the radius of bigger sphere would be equal to what? N raised to, okay, 1 by 3 times r. Suppose n drops, okay, n drops coalesce to form a bigger drop. Okay, so we'll just remember this one. and we'll substitute value of n. So here value of n is 2, it might be 8, it might be 16, whatever it is, we'll just substitute that. Okay. All right, so this is the relation between r, that means the radius of smaller and bigger drop. Then what do we have? So let's say V2 by V1 would be equal to what? Because V is directly proportional to R square. So it is R2 by R1 square. And what is R2? So here R2 would be equal to what? What's our n? N is 2. So 2 raised to 1 by 3 multiplied by R1. Just substitute that here. So what do we get? If we substitute that, it's 2 raised to 1 by 3 times R1 divided by R1 square. R1 gets cancelled. So you have 2 raised to 1 by 3 square. That means 2 raised to 2 by 3. That's the answer. So V2 would be equal to 2 raised to 1 by 3 times of 2 raised to 2 by 3 times of V1. Okay. So it's option C. This is clear. Right, everyone? Okay, so please remember this formula. Which one? Capital R is equal to n raised to 1 by 3 times small r. Okay, let's see next one. Two small spherical metal balls having equal masses are made from materials of densities ρ1 and ρ2. Okay, so two small spherical metal balls, they have equal masses and they are made up of materials having densities ρ1 and ρ2. Okay, and ρ1 is equal to 8 times of ρ2. So ρ1 is equal to 8 times of ρ2. This is given, and radii of 1 mm and 2 mm. So R1 is 1 mm, R2 is equal to, R1 is 1 mm, R2 is equal to 2 mm. They are made to fall vertically from rest in a viscous medium whose coefficient of viscosity equals eta and whose density is 0.1 ρ2. Okay, so fluid's density is very small, it's 0.1 ρ2. The ratio of their terminal velocities would be. So this is very simple, right? What is ratio of terminal velocities? Okay, so it is just V1 by V2. Just write down the formula. V1 by V2 is equal to, tell me, it is 2 by 9 multiplied by its rho minus sigma, right? So what is rho for V1? It is ρ1. And what is sigma? So it is the density of this liquid or the fluid. It is given to be equal to 0.1 times ρ2. Okay, it's given to be equal to 0.1 times ρ2. So ρ1 minus 0.1 times ρ2. Okay, that is sigma, multiplied by, what do you have? It is r square g, or here it will be r1 square g divided by eta. Okay, this is eta. Okay, then similarly next one is 2 by 9. Okay, V2 is 2 by 9, ρ2 minus 0.1 ρ2 times r2 square g divided by eta. This eta gets cancelled, g gets cancelled, 2 by 9 gets cancelled. So what remains is ρ1, which is equal to 8 times ρ2. Let's substitute that. So you have 8 times ρ2 minus 0.1 ρ2 divided by ρ2 minus 0.1 ρ2. So that is 0.9 ρ2, and you have r1 by r2 square. Okay, and that is equal to V1 by V2. V1 by V2, it's equal to 8 times ρ2 minus 0.1 ρ2 is 7.9 times ρ2 divided by 0.9 ρ2. Okay, and what is r1? R1 is 1, r2 is 2. So r1 by r2 is 1 by 2, 1 by 2 square is 1 by 4. So then this rho 2 and rho 2 will get cancelled. Multiply this 0.9 by 4. So it is 3.6. 7.9 divided by 3.6. 7.9 divided by 3.6 is the answer. That is 79 divided by 36. Okay, so there is nothing in the question, this one, no? 79 divided by 36. So question is very simple, right? This is just comparison and they have given some value. So just calculation. Is this one clear? This is from NEET 2019. Right, good. Let's see next one. A small sphere of radius r falls from rest in a viscous liquid. Okay, so a small sphere of radius r falls from rest in a viscous liquid. As a result, heat is produced due to the viscous force, right? Just like frictional force. So as one object slides over another object or some surface, what happens? It has to, we have to do some work against the frictional force. So the work done against frictional force gives rise to what? Heat. That energy is lost, right? So just like that, when some object moves through a fluid, then the viscous force will oppose its motion and work done against the viscous force will be converted to what? Heat. Okay. So the question is the rate of production of heat when the sphere attains its terminal velocity is proportional to. Okay. So rate of production of heat is equal to, you can say, rate of doing work. And what is rate of doing work? Rate of doing work is power, right? It is called as power. What would be power? So power is equal to force times velocity, right? Power is equal to force times velocity. Okay. So here the force is the viscous force and the velocity is terminal velocity. So what is viscous force? It is 6 pi eta r v. Okay, but because velocity is equal to terminal velocity, let's take v suffix t, terminal velocity, multiplied by velocity is terminal velocity. So you have terminal velocity square. Okay, but in options you have r raised to 3, r raised to 5, r raised to 2. That means it is given in terms of radius. Okay, but we have terminal velocity is directly proportional to what? R raised to 2. Okay, so Vt square is directly proportional to r raised to 4, right? So this thing is proportional to r raised to 4 and you have another r over here. So the power is proportional to r raised to 5, right? That is the answer. It's option C. This is clear, everyone? Okay, so this was asked in NEET 2018. Okay, next let's understand the streamline flow and turbulent flow. So what is a streamline flow? So streamline flow means very orderly flow. So just like students, they move in an order, right? Or not students, let's say military. Okay, so army men, they move in an order. So just like that, if particles of a fluid, they move in an order, okay, one follows another and they follow in specific path, then that kind of flow is known as a streamline flow, or it is also called as a laminar flow. Okay, it is called a streamline flow, or it is also called as a laminar flow. Okay, then now if there is disorder, complete disorder in the flow, so in case of flood, suppose the water doesn't flow in a straight direction, what happens? It flows here and there. Okay, there is complete disorder. So then that flow is known as a turbulent flow. Okay, that flow is known as a turbulent flow, right? So this is flow with some velocity. Turbulent flow is flow of water or flow of any fluid with very high velocity. Okay, so here itself you get an idea that streamline flow will be with certain velocity, okay, not that high velocity, and turbulent flow will be with very high speed, very high velocity. This thing is clear? Right. Then after that, suppose you have this pipe and some water is moving or any fluid is moving through this pipe, right? So now if this flow is streamlined, if the flow is streamlined, okay, and the pipe doesn't store any fluid, any amount of fluid, then the amount of fluid that enters the pipe per unit time is equal to the amount of fluid that leaves the pipe per unit time, right? Amount of fluid that enters the pipe is equal to amount of fluid that leaves the pipe. Okay, so from here what do we get is we get A1 V1 is equal to A2 V2. It's equation of continuity. Okay, it is equation of continuity. So let's see how. So see here, this is a pipe and let's say in some time delta t, how much of fluid enters? So delta V is the volume of the fluid that enters. What is the volume? So suppose fluid enters at this point and in time delta t it moves from this point to this point, okay, or you can consider cross sectional area. So it moves from this cross sectional area to this cross sectional area in time delta t, right? So the amount of fluid is delta V, or this is the volume that enters the pipe. So in same amount of time, okay, in same interval of time, not amount of time, what happens? The same volume must leave the pipe also. Okay, if this does not happen, then there will be some storage of fluid in the pipe, right? Okay, if fluid is continuously moving, then the pipe won't store any amount of fluid. Okay, fluid is continuously moving through the pipe, right? So therefore what we can say is the volume in would be equal to volume out. The volume that enters in some time is equal to volume that leaves the pipe in the same amount or same interval of time. Okay, so volume that enters here in some time delta t, suppose it moves through this much distance, and volume that leaves from here in some time delta t in the same interval of time, it moves through this much distance. So this is S2, this is S1, this is S2, right? So what would be the volume that enters in time delta t? It will be area multiplied by this length. Okay, it will be equal to area multiplied by this much length. Okay, so it is A1 S1 is the volume that enters and A2 S2 is the volume that leaves, right? Then how can we write S1? So speed is equal to distance covered divided by time, and therefore the distance covered is equal to speed multiplied by time. So it is V1 times delta t. Okay, what is S2? It would be V2 times delta t. So suppose speed at this point and this point is different, then you can cancel out delta t, and then what do you get is A1 V1 equals to A2 V2. Very, very important relation. This is known as an equation of continuity. Okay, if flow of fluid through a pipe is continuous, then A1 V1 is equal to A2 V2. Is this in clear, everyone? Okay, good. So this is known as equation of continuity. All right. So now this equation is followed by a streamline flow. Okay, this equation is followed by streamline flow. Okay, so now these are some points of separation between streamline flow and turbulent flow. Can you see that, or it's very, very very thin? Okay, so see, streamline flow the smooth flow of a fluid with velocity smaller than a critical velocity. We'll see what is critical velocity. Okay, it is limiting value of velocity, is called as streamline flow. Okay, in streamline flow, the velocity of fluid at given point is always constant. Okay, if you take some point, certain point, so what does it mean? It means that suppose take this point, so one particle of fluid or one molecule, you can say one particle of fluid, it moves through this point with, let's say, 5 meters per second. Then the particles, all particles that are following this particle, they will attain velocity of 5 meters per second at that point, and from this point they will move by the velocity of, okay, with the velocity of 5 meters per second, right? So at a particular point, velocity of all particles that are passing through that point would be same, it would be equal. Okay, then two streamlines can never intersect because they define the path of flow of fluid. Okay, so they are always parallel, so two streamlines can never intersect, and streamline flow over a plane surface can be assumed to be divided into certain number of layers, so that's why it is also known as laminar flow. Okay, all right, so these are some properties of streamline flow. And similarly, not similarly, actually in contrast with that, there are some properties of turbulent flow. So what are those properties? What is turbulent flow? The irregular and unsteady flow of a fluid when its velocity increases beyond critical velocity. Okay, so it increases beyond certain velocity, then the flow becomes turbulent, right? Then in turbulent flow, the velocity of fluid at any point does not remain constant, so it is nothing like the streamline flow. Okay, so in streamline flow it remains constant, and in turbulent flow it does not remain constant. In turbulent flow, at some points the fluid may have rotational motion, okay, which gives rise to eddies, right? So you know eddies, okay, eddies in river. So if flow is turbulent, then it can give rise to rotational motion and it gives rise to eddies. Okay, a flow tube loses its order and particles move in random directions. So we have seen this. Okay, so these are some properties of turbulent flow, right? So then there was a mathematician called Reynolds who found certain criteria, okay, who found the value of a velocity above which this flow will become turbulent. So he found a number particularly called as the Reynolds number. Okay, it is Reynolds number. What is Reynolds number? We can write it in this way. So R is equal to Reynolds number. R is equal to the inertial force divided by viscous force. Okay, what is inertial force? Suppose you take a pipe, you consider this pipe, then why does the fluid flow in the first place? Why does the fluid flow through that pipe? Okay, so if you consider this pipe, why does the fluid flow through this pipe? It's because of the pressure difference. Pressure on this side would be more compared to that of pressure on the other side. Okay, so what is the inertial force? There is some pressure on this side, let's call it P1. There is some pressure on this side, let's call it P2. So the fluid flows from the place of higher pressure to lower pressure, right? Okay, so if there is more pressure difference, then the fluid will flow with more velocity. Okay, if there is more pressure difference, that means the fluid will flow with higher velocity, and that's why it might give rise to what? It might give rise to turbulence. Okay, what opposes that? So this gives rise to turbulence, and what opposes that is a viscous force. Okay, so different layers. So see, the first layer which is in contact, first layer meaning the layer which is in contact with the pipe, that moves with slowest velocity. Okay, the layer of the liquid that is in contact with the pipe, it moves with lowest velocity. The layer which is in contact with that layer, it will move with little bit higher velocity. Okay, then the layer which is in contact with that layer. Okay, so as you go inside the pipe, what happens? So I have a picture for that. So now consider flow of fluid here. So the layer of fluid which is in contact with the pipe, it moves with lowest velocity. Okay, it is slowest. Then as you move inside, what happens? The layers of fluid gain more velocity. Okay, so they move with higher speed. So you can see here, starting from the same point, suppose this fluid, it starts at the same point, but the fluid which is at the center, it will move larger distance compared to the fluid which is at the ends. So it will form a pattern like this. This thing is clear? Yes, no? Okay. So the viscous force, it opposes the turbulence, right? It won't let the fluid flow in any direction with very high velocity. Okay, it restricts the velocity, and that's why it's in denominator. The inertial force is in numerator, viscous force, it opposes the turbulence, that's why it is in denominator. Okay, so now there are a lot of calculations in this. Okay, and the Reynolds number will come out to be equal to rho times Vd by eta. Okay, it is rho times Vd by eta. So suppose V is the speed of fluid. Okay, rho is the density, of course, of the fluid. D is diameter of this pipe at certain place. It can have different diameters at different places, but at certain place diameter is suppose D. Okay, right, because you can have a pipe whose diameter is not constant. Okay, it's like this. Okay, and eta is the viscosity, coefficient of viscosity. So Reynolds number is calculated in this way. Okay, so then if Reynolds number is less than 1000, then the flow is streamlined. Reynolds number is in between 1000 and 2000, then it is a streamlined flow which might turn turbulent at some point. Okay, and if Reynolds number is greater than 2000, the flow is turbulent, right? So we just need to remember this criteria. If Reynolds number is less than 1000, the flow is streamlined. If Reynolds number is in between 1000 2000, flow is streamlined. It might turn to turbulent flow at some point. Okay, and if it is greater than 2000, the flow is definitely turbulent. This thing is clear, everyone? Okay, and based upon that, there might be a question that find out the critical velocity for certain fluid. So you will put Reynolds number equal to 2000, then coefficient of viscosity might be given, rho and d might be given. Okay, or there might be a question in this way, the critical velocity for this much velocity, not critical velocity, for this much velocity, suppose, determine if the flow is streamlined flow, turbulent flow, or it is a streamlined flow which might turn to turbulent. Okay, this thing is clear? All right. So this is the Reynolds number. Okay, there haven't been many questions based upon this thing, but there can be, we don't know, right? Okay, then comes very important theorem. It is the Bernoulli's theorem. Okay, and what is that? For a streamlined flow of a fluid through a pipe, sum of pressure energy, potential energy and kinetic energy per unit volume remains constant. So we need to remember this formula. Okay, we'll see how does it come, but we need to remember this formula, that sum of pressure energy, okay, pressure plus rho gh, this is kinetic energy, sorry, this is potential energy per unit volume, plus half of rho times v square. This is kinetic energy per unit volume. So sum of these is constant, right? Sum of these is constant. Okay, this is the Bernoulli's theorem. Okay, pressure plus rho gh plus half of rho into v square is equal to constant for a fluid. All right, so let's see where does it come from. So suppose this is a fluid moving through this pipe. Okay, this is the fluid moving through this pipe. So now pressure at this end is suppose P1, it's moving in this direction, means pressure from this end must be more. Then pressure from this end is suppose P2. So how much is the force at this end? Force at this end would be pressure multiplied by area, so it is P1A1, right? So if you consider a small section of the fluid, let's say if you consider this much section of the fluid, what happens is the fluid from this side is exerting a force in this direction on that section, and fluid which is ahead of it, okay, fluid which is here, it exerts a force in the opposite direction, right? So how much would be the force from this direction? Force from this direction is P1A1, right? Force from this direction would be P2A2. Okay, so then now we need to find out how much would be the work done on this fluid due to these two forces. Okay, so velocities at this point and that point are different. That means in some time delta t, what will happen? The fluid will cover different distances. Okay, fluid will cover different distances. So here distance covered is delta S1. So force is what? Force is equal to P1A1. So therefore the work done on the fluid is equal to P1A1 times delta S1, right? And on this end force is opposing. So force is, you can say, minus P2A2. Okay, and against that force the fluid is moving with some velocity v2, so it covers distance equal to delta s2, which will be equal to v2 multiplied by delta t. So the work done in this case would be equal to minus of p2a2 times delta s2. Okay, p2a2 is the force. Is this thing clear, everyone? Right, good. So then work done due to the pressure or due to pressure difference, you can say, okay, it's equal to P1A1 delta S1 minus P2A2 delta S2, right? And then volume entering is equal to, you can say, A1 times delta S1, this is delta V1, this is volume entering. Volume leaving is equal to A2 times delta S2, and this is delta V2. So this is volume entering A1 times delta S1, okay, and volume leaving is A2 times delta S2. What we can do is we can substitute here, this is volume entering and this is volume leaving, and for a streamline flow this is equation of continuity, that volume that enters is equal to volume, the amount of volume entering is equal to amount of volume leaving, and that's why delta V1 is equal to delta V2, and suppose it's equal to delta V. This thing is clear, everyone? Right, and therefore you can say that this is delta V, this is also delta V. So you have P1 times delta V minus P2 times delta V. You can take delta V common, so what remains is P1 minus P2. So you have P1 minus P2 times delta V. Okay, all right. So then now this work done is equal to, we can say it's equal to change in energy. Yes, no? Okay, I can just say that this work done is equal to change in energy. Okay, and I can directly say, instead of doing all this calculation, I can just directly say that this work done, okay, work done is equal to change in mechanical energy, right? So work done is equal to, we have just seen it's P1 minus P2 times change in volume, it's equal to, or not change in volume, the volume, okay, it's equal to change in mechanical energy. So you can say final mechanical energy means final kinetic energy plus potential energy, Ke2 plus Pe2 minus Ke1 plus Pe1, okay, because its height is also changing, right? Work done is equal to change in energy, right? So then you can, what you can do is you can substitute kinetic and potential energies, right? Before that I will move this delta V on that side. So I get P1 minus P2 is equal to P1 minus P2 is equal to Ke2 minus Pe2, okay, minus Ke1 plus Pe1 all divided by volume, okay, all divided by volume. So in formula of potential energy you will have mgh. If you divide that by the volume, okay, let's have mass equal to delta m. If you divide that by volume, then what do you get? You get the density, right? Yes, no, you get the density. This thing is clear, okay? And therefore here what you will get is kinetic energy per unit volume, okay, I am taking volume on that side, so it is kinetic energy per unit volume, so it is half of rho times v square, okay, but this is kinetic energy at point 2, so it is half of rho times v2 square plus potential energy at point 2 is mgh divided by you have volume, so it is potential energy per unit volume, so it is rho gh at point 2 minus, similarly you have half of rho into v1 square plus rho g h1, right? And then I will move this thing on this side and P2 on that side. So what do I get is P1 plus, okay, P1 plus rho g h1 plus half of rho into v1 square is equal to P2 plus rho g h2 plus half of rho into v2 square. Okay, so what we have used is just conservation of energy. And then what you get is the Bernoulli's theorem. Okay, so these 2 points can be any 2 points, and therefore what we can say is pressure plus rho gh, that is potential energy per unit volume, plus half of rho times v square, it's constant for a fluid in streamline flow. Right, is this thing clear, everyone? Yes, no? Okay, good, very good. Then one more thing, we saw equation of continuity that A1 V1 is equal to A2 V2. Okay, so product of area times velocity of a fluid remains constant. So what does that mean? It means that if area is small, velocity would be more. If area is large, velocity would be less. Right? If area is small, velocity would be more. If area is more, velocity would be less. This thing is clear? Yes, no? Okay. So one example of that can be a shower, right? Which is very important in this season. Okay. So in case of shower, what happens? Liquid, not liquid, water moves through the pipe, and then it moves through a pipe which has some area, and then it comes to that shower. Okay, so now our shower has small holes, so collective area of those small holes is smaller compared to that of the area of the pipe, and therefore a water it comes out with very high velocity. Okay. So now let's consider some examples of Bernoulli's principle. One is design of an aerofoil. What is aerofoil? So you have seen aeroplanes, right? So the shape of wing of an aeroplane, it has a particular shape. Wing of an aeroplane has a particular shape. It is known as aerofoil. Okay, it is known as what? Aerofoil. So its shape is like this. Okay, its shape is like this. Can you see this? Now what happens because of the shape is, see, the height of this point and this point, you can consider it to be equal. The height of this point and this point is equal, almost equal, you can say, right? There is not much thickness of the wing is not much, and the density of air is also not much. So if we make use of Bernoulli's principle, that P1, let's say 1 is this surface area. Okay, this is surface area 1, and this surface area at the bottom, it is surface area 2. Okay, so then you have P1 plus rho g h1 plus half of rho into v1 square is equal to P2 plus rho g h2 plus half rho v2 square, right? So now see, the density of air is not much, so there is little bit of height difference between the point at top or surface at the top and surface at the bottom of the wing, but that's not much. Okay, so this term would be very, very small, so you can just neglect this term, and what remains is P1 plus half of rho into v1 square is equal to P2 plus half rho v2 square. Okay, so now when aeroplane moves like this, okay, so then the wing is designed in such a way that velocity on one side, okay, velocity on one side would be more compared to that of velocity on the other side. It will be easy for the air to flow on one side compared to that of another side. Okay, this thing is clear, right? So if velocity is more here, so see, P1 plus kinetic energy per unit volume, this thing is constant. If height is same, then P1 plus kinetic energy per unit volume is a constant. So that means if velocity is more on this side, then what will happen? Pressure will be less. Okay, if velocity is more on this side, that means pressure would be less. If pressure is less compared to that of pressure at the top is compared to that of pressure at the bottom, then what will happen? It will get a lift. Okay, so this is how, right, this is how the aerofoils are designed. This thing is clear, everyone? Okay, so this is one example. Then now if there is wind blowing with very high speed, okay, so suppose it happens sometimes that wind blows with very high speed, and you might have seen or you might have heard at least in news that the roofs of some huts, okay, some homes, they are detached and they fly away if wind blows with very high speed. Okay, right? So why does that happen? It happens because, again, if it flows with very high speed, so see, there would be some pressure of the air above this roof and some pressure of the air below the roof. Okay, so wind is blowing, that means air is moving with very high speed here, and air inside the house, okay, inside that home or that room, let's say, air here it's steady, air is not at all moving. So if if velocity is less, then pressure would be more, because sum of pressure and kinetic energy per unit volume it is constant, right? The height of this point and this point, you can say it's same. Okay, thickness of the roof is very small. Okay, so height doesn't matter, right? So then velocity here is 0. That means there would be huge pressure built in huge pressure difference built between these two surfaces pressure outside would be very less. I'm sorry. Pressure outside would be very less compared to that of pressure inside, and that's why this roof would be pushed. Okay, there would be net upward force on the roof, and that's why roof is detached and it flies away. So this thing is clear. Okay, good. So these are some applications of Bernoulli's theorem. I mean, these are some phenomena which can be explained by using Bernoulli's theorem. Okay, so this is not an application. Okay, this disaster happens because of the Bernoulli's principle. All right, let's see next one. Next one means next application. This is an application. This is a disaster. Let's see next application. It is Venturi meter, or you can say Venturi meter. I don't know. Venturi meter. Now, what is this thing? This is a device. It is used to measure the flow of speed, okay, of fluid in a pipe, right? It's a device which is used to measure flow speed of fluid in a pipe. So, how does it look like? It looks like this. Anyways, suppose this is a pipe. The Venturi meter is connected to the pipe. It has variable cross section. Okay, so cross section here would be just same as that of cross section of the pipe. Okay, and the cross section here has very small area. So suppose area over here is capital A, let's call it A1. Okay, let's call it A1 and A2. This is small a. So just remember capital A or A1 is the bigger area, or it is area of the pipe, and A2 is the area of narrower end of the Venturi meter. Okay, so now fluid is flowing, any fluid, it might be any fluid, oil, or it might be water, right? So it is flowing with some speed in this pipe. Now, will it flow with same speed, lesser speed, or higher speed through this area? Tell me, lesser, higher, same speed? Higher speed, right? Because this area is small. Okay, all right. So then now the pressure is measured using this manometer. Okay, so a manometer is also connected to the Venturi meter, or you can say it's part of Venturi meter. So mostly it is used, mercury is used in this manometer. Okay, but sometimes they might give you the density of the fluid that is used in the manometer. Okay, so you can easily measure the pressure difference here and here using what? The height difference at two places. Okay, height difference of the mercury at two places, right? So pressure difference at A1 and A2 is just equal to what? The density of mercury times G multiplied by H. Okay, so we are using mercury. If something else is given, we can make use of that. Okay, there is no issue, right? We can just change density of mercury with density of that fluid. So then you get P1 minus P2 is equal to rho m into GH, and sorry, the height at this point is equal to height at this point. Okay, there is no difference in height, so we can neglect this one term. Okay, this term rho GH in the Bernoulli's theorem or Bernoulli's principle. Okay, and therefore what would be this pressure difference? So pressure difference would be just equal to the difference in kinetic energy per unit volume at those two places. This thing is clear? Yes, no? Okay, because height is same, and then we can derive this formula. Okay, we can derive the formula, but now I mean this formula you don't need to remember. So see, V1 is the speed of the fluid at this end. Okay, V1 would be equal to square root of 2 times rho mgh divided by rho. So now what is rho m? It is density of the liquid that is used in the Venturi meter. And what is rho? Rho is the density of this liquid. Okay, times a1 by a2 square minus 1 raised to minus half, means this term would be in denominator. Okay, so raised to minus half. What is a1? a1 is the area of this end, and a2 is the area of smaller cross section of the Venturi meter. Okay, so formula is quite complicated. Personally, I don't remember it, and without remembering it also we can solve all of the problems based on Venturi meter just by using the Bernoulli's theorem. Okay, the Bernoulli's principle. All right, then if you want we can see derivation of that, but I don't think it is important. But see, consider 2 points in the Venturi meter. Which 2 points? This one, or this point and this point. Okay, so pressure at this point plus kinetic energy per unit volume at this point would be equal to pressure at this point plus kinetic energy per unit volume at this point. Why? Because height is same, so potential energy per unit volume is equal, right? So P1 plus half of rho into V1 square is equal to P2 plus half rho into V2 square. This is from Bernoulli's theorem, right? Then you can move P2 on this side, so you get P1 minus P2 is equal to half of rho into V2 square, and then you move this thing also on other side, so it is half of rho times V1 square. You can take rho common, half rho common here. Okay, so you get V2 square minus V1 square. Okay, so that is P1 minus P2. Okay, and what is P1 minus P2? It is rho m times gh. You can substitute that. Okay, so P1 minus P2 is rho m times gh. You can substitute that. Then you can move this rho and this 2 on other side, so you get 2 times rho m gh divided by rho. Okay, so looking similar to what we saw just now. Okay, this formula. So see, then what you do is you make use of equation of continuity. So a1 v1 is equal to a2 v2, and you substitute that v2 is equal to a1 divided by a2 times v1, right? v2 would be equal to a1 divided by a2 times v1. You substitute that here. Okay, you substitute that here because v2 would be more. So it is a1 by a2 times v1 square minus v1 square is equal to this term on right hand side. Then you take v1 square common. Okay, what remains is a1 by a2 square minus 1, and then you move it on other side, so v1 square would be equal to this thing divided by that thing. Okay, so that is 2 times rho mgh divided by rho. Okay, divided by this thing that you are taking. Okay, you take v1 square common and remaining part you move on the other side. So what remains is a1 by a2 square minus 1, and then you take the square root, so you get this formula. Okay, this is the derivation. If you understood, that's very good. Even if you didn't understand, and if you want to understand it, you can see the video later, but I don't think you need to remember this one. Okay, that's my opinion, because the equation is complicated and just using this formula we can solve it. Okay, at any given time, right? Okay, so this thing is clear. How to measure the flow of fluid using Venturi meter? Yes, no? All right, very good. Then let's see next application of Bernoulli's theorem. There are lots of applications. Next is Torricelli's law. Torricelli's law of flow of efflux. Okay, for the flow of efflux. What is this efflux? So efflux means liquid coming out through a small opening. That small opening has also got a name. It is called as orifice. Okay, so suppose we have a tank like this. Okay, we have a tank like this, and it might be closed tank, it might be open tank, so we need to be careful here. And generally this law is okay, this law would be true for both the tanks, right? But then the formula would be different for both of them. Okay, so it might be closed tank, it might be open tank. So then see, The tank has huge surface, huge area of cross section. Okay, this is cylindrical tank. Its area of cross section is very high, and there would be small tap. Okay, maybe at this height, maybe at the bottom somewhere. So compared to this area is very small. So that's why it is known as an orifice. That's a small opening. This thing is clear? Yes, no? Okay. And what is efflux? Efflux is the flow speed of the fluid that comes out of an orifice. Okay. So again, the velocity of efflux or the speed of efflux, that is the liquid that is coming out of orifice, is given by this formula. V is equal to square root of 2gh plus 2 times of P2 minus P1 divided by rho. What is P2? What is P2? P2 is P2 is the pressure at this end. That means pressure at the orifice. What is P1? P1 is pressure at this end. Okay, that is pressure at top. Okay, divided by, you have rho. Rho is density of the fluid. Okay, so this is the formula. And if pressure at these 2 points is equal, so this end is open, means pressure at that end is equal to what? Atmospheric pressure. Okay, air pressure. If this end is also open, okay, if this end is also open, then pressure at this end would also be equal to what? Atmospheric pressure. So if both pressures are equal, then you can just cancel it out, cancel out the second term. So what remains is V is equal to square root of 2gh. So what is Torricelli's law? Torricelli's law is that okay, so Torricelli's law says that suppose you have some open tank and you have some orifice, that means you have some tap at the bottom of that tank somewhere. Okay, and the height of the liquid column is suppose h. What is h? Height of liquid column above the orifice. Okay, then the speed of the fluid that comes out of that orifice is just equal to that of it's just equal to square root of 2 times gh, and it is just equal to, you can say, the speed of any object which is released from a height h. Okay, any object in free fall which is released from height h. So this is Torricelli's law. Okay, the speed of efflux through an orifice is just equal to the speed of any object which is released from the same height as that of the height of the air column above the orifice. This is the Torricelli's law. Is the law clear? Yes, no? Okay, good. So this is Torricelli's law. So equation for Torricelli's law would be this one, and this is applicable for, it is applicable for an open pipe. Tank is open. Okay, but for closed pipe this would be the formula, right? So now we can prove it very easily, right, by just by using the Bernoulli's principle, Bernoulli's theorem. Okay, so see, what do we have? So here at this end, at the top, the fluid is steady. The velocity of fluid is so small that it's almost zero, you can say. How? Because this area of this tank is so big compared to that of this area, and you have equation of continuity that A1V1 would be equal to, see, the water is coming down, or any fluid that is filled, it is coming down with some velocity V1 suppose, okay, here, and it's coming with velocity or speed V2 at this end. So it must follow the equation of continuity, that is A1V1 is equal to A2V2, and this area is very big, that means velocity here would be very small. Okay, so if A1 is so very big compared to that of A2, then V1 would be very less compared to that of V2, and therefore we will just neglect V1. We just neglect V1, and then we write the Bernoulli's theorem, that V1 plus half of rho into V1 square. We neglected V1, so that term is neglected, plus rho g h1 is equal to P2 plus rho g h2 plus half of rho into V2 square, right? And then next what you can do is just move these two terms on this side. So what you get is P1 minus P2 plus rho g H1 minus rho g H2. Okay, it is half of rho times V2 square. So P1 minus P2 plus rho g H1 minus H2 is half of rho into V2 square. Okay, and then you can just divide this right hand side by rho. What you get is V2 is equal to square root of 2 times P1 minus P2. Okay, square root of 2, what did I say? Square root of 2 times P1 minus P2 divided by rho plus 2g H1 minus H2, and H1 minus H2 can be written as H. Okay, this thing is clear, everyone? Right? Okay. Oh, here I wrote P1. Okay, this was P1, this was P2. It has to be P1 minus P2, not P2 minus P1. So let me correct this one. Okay, it has to be P1 minus P2, right? Okay, so then you get this formula, which is the first formula that we saw, and this is for a closed tank. For a closed tank, you should use this formula. If tank is open, then P1 is equal to P2 is equal to atmospheric pressure. So this term gets cancelled out, and what remains is P2 is equal to just square root of 2g times H1 minus H2. Okay, the height difference, right? And this is called as Torricelli's law. Is there any doubt in this? Yes, no? Anyone? No doubt? Right. Okay. So now let's see some problems based upon this thing. Let's see this one. This is from NEET 2023. Okay. And the Venturi meter works on. So this is the kind of problem they asked in NEET 2023 based on Venturi meter. Huygens principle, Bernoulli's principle, the principle of parallel axis, the principle of perpendicular axis. Okay, so it is based on the Bernoulli's principle, right? So these are 3 marks, right? Anyways, let's see next one. Okay, the cylindrical tube of a spray pump. So spray pump, it works on the Bernoulli's principle, right? It has radius r, one end of which has n fine holes, okay, each of radius small r. If the speed of the liquid in tube is v, then the speed of ejection of liquid through the holes is. So this is your spray pump, something like this. Okay, and it has got some area here, area of cross section, and the radius over here is r. Then it will have some tube like this and small thin holes like this. Okay, so now see here the speed, your liquid, okay, it goes up from here, it goes up with speed v, suppose. Okay, it comes out from here with some speed, that speed we want to find out. So it is based on equation of continuity, right? So area here is suppose A1, area here is suppose A2. So what you can say is A1 V1 is equal to A2 V2. Okay, so A1 V1 is equal to A2 V2, and what is A1? So it is pi r square times V1 is equal to A2 V2. We want V2, no? So let's move A2 on other side. Okay, so let's write pi r square times V1 is equal to A2. There are n fine holes, okay, n small holes. So it is n times of pi multiplied by small r square times V2. and then pi gets cancelled out. Okay, pi is cancelled out, and what remains is you can move this n times of r square on that side. What do you get? You get v2 is equal to capital R square divided by n times of small r square times of v1. So that's your answer. Okay, v1 is capital V, so v times of r square divided by n times r square. To option D. Okay, right, it's option D. This is clear. Everyone? Okay, simple problem, right? Let's see next one. Assertion: for Reynolds number Re greater than 2000, the flow of the fluid is turbulent. Okay, we know that. Yeah, so this is true. And reason: the inertial forces are dominant compared to that of viscous forces at such high Reynolds number. So is this correct? Yes, no? So Reynolds number is high. What is Reynolds number? We saw it is ratio of the inertial forces, inertial force to the viscous force. Okay, it is greater than 2000 means it's high Reynolds number. High Reynolds number means the numerator is more compared to that of denominator. So inertial forces are more compared to that of non-inertial, viscous forces. Right? This is clear? Yes, no? So assertion and reason both are correct, and reason is the correct explanation of A. Okay, straightforward, right? Okay, good. Let's see next one. A small hole of area of cross section 2 mm square is present near the bottom of a fully filled open tank of height 2 meters. Okay, this is open tank of height 2 meters. So Torricelli's law should click, right? Taking g equals to 10 meters per second square, the rate of flow of water through the open hole would be nearly. Options are in meter cube per second, right? That means they are asking about the volume coming out per unit time. This is from NEET 2019. Tell me, volume that's coming out. Okay, first of all, you can find out, see, this is fully filled open tank of height 2 meters. That means what would be speed of efflux? Speed of efflux, P is just square root of 2gh. Okay, just find it out. So it is equal to square root of 2 times 10 times h is also 2. So it is 2 root 10, right? 2 root 10. Okay. Can we do better here? And they say take g is equal to 10. So v is equal to square root of 2gh. H is 2 meters. No. So it's 2 root 10 meters per second. All right. And then after that, so what is the rate of flow of water? Okay, rate of flow of water means the volume that's coming out per unit time. Okay, rate of flow of volume, this is volume, okay, capital V. So that is d by dt of area times S. Okay, area you can take out, it is just equal to ds by dt, and that means it is equal to area times velocity, right? It is a times ds by dt. that is area times velocity. Area times velocity. So velocity is 2 root 10 that you just found. And what is area of cross section? Area of cross section of the efflux, orifice is 2 mm square. Okay. So 2 multiplied by 10 raised to minus 6 multiplied by, you have 2 root 10. So that is 4 root 10. And root 10 is roughly equal to, you can say 3.3 or something like that. Or no, it is 3.14, 3.1 something. Okay. Then you have this thing multiplied by 10 raised to minus 6. So 3.1 times 4 is 12.4. Okay. 12.4 into 10 raised to minus 6. 12.6 into 10 raised to minus 6. That is the answer. Okay. Meter cube per second. It is option B. Right. This thing is clear, everyone. So you just need to find out speed of efflux, and then the volume coming out per unit time is given by just area times the velocity. Okay. The rate of flow of fluid is area times velocity. Right. Okay. Let's see next one. A wind with speed of 40 meters per second blows parallel to the roof of a house. Okay. Wind is blowing parallelly to the roof of a house. The area of the roof is 250 meters square. Okay. So this roof is going to fly away. Assuming that the pressure inside the house is atmospheric pressure, the force exerted by wind on the roof and the direction of force will be. Tell me. So pressure inside the house is atmospheric pressure. What would be pressure outside? This is the house. Wind is blowing like this. Okay. Parallel to the roof. Right. So you can say pressure inside is P1, that's equal to atmospheric pressure. Pressure outside would be equal to P2, right? So make use of this thing, P1 plus half of rho into V1 square, Bernoulli's theorem, is equal to P2 plus half rho V2 square. But the air inside the house, it is not at all moving, so V1 is 0. Okay, V1 is 0, and therefore what is P2? So P2 is just equal to P1 minus half of rho multiplied by V2 square. Okay, but they didn't ask you about the pressure, they are asking about the force, right? So what will be force? It will be equal to P1 minus P2 multiplied by the area. Okay, that's the pressure difference. Force would be equal to P1 minus P2 multiplied by area. So P1 minus P2 is half of rho times V2 square. So the force, which is equal to pressure difference multiplied by area, would be equal to half of rho times V2 square multiplied by area of cross section is A. So just substitute the values. So half of density is 1.2 kg per meter cube. Okay, 1.2 kg per meter cube multiplied by V2 square is 40 square multiplied by area is 250. Okay, so 250, this thing is 40. How much is it? This is 2.4 times, you have 40 times 40 times 250. Okay, let's multiply this out. So this is 250 times 4 is 1000. This would be 10,000. 10,000 times 24, this is 9.6, 9.6, 96, 96 times 10,000. Okay. Oh, what did I do? It was half. That's great. I multiplied by that too. Okay, so I didn't see 1. Anyways, so 1.2 divided by 2 is 0.6. 0.6 multiplied by, you have 40 times 250 is 10,000, right? So this would be 0.6 times 40 is 2.4, no, 24 multiplied by 10,000, so it is 2.4 into 10 raised to 5, right? That's the answer. So upwards or downwards, tell me. Upwards, because pressure inside is more compared to pressure outside, right? This pressure difference is positive, means P1 is greater than P2. Okay, so the net force is upwards. Okay, so it is 2.4 multiplied by 10 raised to 5 upwards. This is the answer. Simple. Yes, no, everyone? Okay, good. All right, let's see next one. An incompressible fluid flows steadily through a cylindrical pipe like this, okay, which has radius 2r at point A and radius r at B further along the flow direction. If the velocity at point A is v, the velocity at point B is very simple. You just need to apply what? Equation of continuity, that A1 V1 is equal to A2 V2. So A2 V2 is equal to A1 V1, and then move A2 on that side. So what do you get is V2 is equal to A1 divided by A2 multiplied by V1, right? So this area is directly proportional to radius square. So radius here is 2r, radius here is r. So A1 is pi multiplied by 2r square, A2 is pi multiplied by r square, okay, times V1. Pi gets cancelled, r square will get cancelled. You have 2 square times V1 means 4 times of V1. So that's the answer, 4V. It's option D, right? Yes, very simple. Okay, right? Okay, good. Let's see next one. Water flows steadily through horizontal pipe of variable cross section. If pressure of water is P at a point where the flow speed is V, pressure at another point where flow speed is 2V, okay, is pressure at another point where flow speed is 2V is. So again, this is based on the principle of continuity. So no, Bernoulli's theorem, I said continuity. Yeah, continuity is applicable. What do we need to use here? P1 plus half of rho into V1 square, Bernoulli's theorem, is equal to P2 plus half of rho into V2 square. So why I didn't write rho GH or rho GH1, rho GH2? It's because this is a horizontal pipe. So height at those 2 points would be equal. No need to write down the height term, right? Rho GH. Okay. And therefore you want what? Pressure at another point where the speed is 2V. So we want P2. So let's put the values. P1 is P1, or let's say P1 is equal to P plus you have half of rho times V square is equal to P2 plus this is half of rho times 2V square. Okay, V2 is equal to 2V. Let's move this term on this side. What do we get? You get P2 is equal to P plus half rho V square minus half rho 2V square is 4 times of V square. Okay, so rho V square you can take common, then 1 minus 3, 1 minus 4 is 3, 1 minus 4 is minus 3, right? So this thing is minus 3, and what you get is P minus 3. Okay, from here what you get is you can take half rho V square common. So from this term 1, from this term you get minus 4, 1 minus 4 is minus 3. So P minus 3 times half. So let's write 3 by 2 rho v square. So that's your answer. It is option A. Right, Vishalini already said it's option A. This is clear, everyone? Okay. All right, good. Let's see next one. A fluid is in a streamline flow across a horizontal pipe of variable area of cross section. For this, which of the following statements is correct? So tell me which one is correct. The velocity is maximum at the narrowest part of the pipe and pressure is maximum at the widest part of the pipe. Okay, so if you just write down the Bernoulli's theorem, so P1 plus half rho V1 square would be P2 plus half rho V2 square, and the equation of continuity A1 V1 is equal to A2 V2. So from this equation we know that if the pipe is narrow at some point, then the speed would be more. Okay, because area times speed is constant. If area is small, speed would be more. So this thing is correct, and pressure is maximum at the widest part. So now if part is wide, okay, that means area is more. Area is more means speed would be less. If speed is less, that means pressure would be more. So this one itself is correct. Okay, option A itself is correct. This thing is clear. Right, good. Let's see other options too. Velocity and pressure both are maximum at, no, this can't be correct. Velocity and pressure both are maximum at widest part, no. Velocity is minimum at narrowest part of the pipe and pressure is minimum at the widest part, so they just wrote it opposite way. Okay, so this one is correct, right? Okay, let's see next one. A liquid is allowed into a tube of truncated cone shape. Identify the correct statement from the following. So the speed is high at the wider end, not correct. The speed is low at the wider end and high at the narrow end. This one is correct. Okay, very simple. The speed is same at both ends in streamline flow. No. The liquid flows in uniform velocity in the tube. No. Okay, so option B is correct. Very simple.